Well, I'm trying to switch on my camera, which does not work as expected. Okay, now it's good. So, hello again. Are there any questions to the example I have carried out here? If that was not the case, I would like to carry out one more calculation that is something which we need later, but anyway, I have been also asked yesterday during consultation for a similar kind of problem. So we will now find out the total current flowing through a cylindric conductor with non-homogeneous current density. We have a conductor of circular cross-section with the diameter of A. And now we have there a current density flowing inside the paper that we denote by X, and this current density depends on the radius, on the distance from the center of the conductor. In our case, the current density J is B plus dr plus cr squared. So it's a quadratic function, b plus dr plus cr squared. And we should figure out the total value of the current, which is an integral of the current density. So we know that current I is an integral over the cross-section of a dot product of current density and the element of the cross-section ds. Well, this is quite simple. In our case, the cross-section and the current density have the same direction, or those vectors are collinear, and therefore we can switch from a dot product to a simply multiplying J ds. Now, there is still one point that I would like to address, which is important. We will carry out the integration. Well, you could do that within Cartesian coordinates, but you would get very crazy low and up limits in 2 dimensions. So possibly we tend in cylindrical coordinates to make the integration from the center to the surface of the conductor and clockwise or anti-clockwise around. Now this is very important, and there is a common mistake which is done there. Well, first, again I repeat the idea of integral solutions. We take a small differential, a small piece of the problem that is so small that the flux or the field or the property we integrate can be considered homogeneous within that region. I will multiply this region here to be seen easily. So we have a kind of element that is very small, so that we have here a differential angle d alpha, say in this direction, and it's very small. And we have here a difference in radius dr, which is also very small, so that we can somehow consider this area like bearing homogeneous current density. Now, the common mistake that is done at this moment is that we say, okay, and what the surface of this element is. We have dr here and the alpha here. So it somehow seems that the area is d alpha times dr, but that's not the true. Just consider that we have something like a pi from a cake, which has a sharp edge here and gets big here. So if you have the elements, the surface of that element depends on the radius at which it is positioned. So this something has a surface, an area of dr d alpha multiplied by the radius. We have the good luck that the element is so small that we can consider one radius for all of it. So let's mark it something like this. We have the radius r. But anyway, the element is this. This is ds. So now we can rewrite the integral like an integral from 0 to a, that's integrating against r, an integral from 0 to 2 pi, that's integrating around the circle, j, and when substituting ds by dr d alpha, we do not have the possibility to omit r, so r dr d alpha. Now we can substitute this expression for the j, and therefore we get an integral from 0 to a, an integral from 0 to 2 pi, b plus dr plus cr squared r d alpha dr. Well, and we are more or less done. First, the integrand does not depend on the angle alpha. So I can carry out the integration, and the result is just multiplying this by 2 pi. Second, the rest of the integral depends on r, so I will have to make it step by step. I will first integrate rb and get r squared b divided by 2. No objection? Then I will get the dr squared, which I integrate and get dr raised to the third order divided by 3. And then I integrate CR raised to the third order and get CR raised to the fourth order divided by 4. Then I substitute lower and upper bounds. The lower bound, when substituted to the expression, gets 0. So in fact, I can directly make the integration as I have been reading and just substitute a. So that would be 2 pi multiplied by ba squared divided by 2 plus dA raised to the third order divided by 3 plus Ca raised to the fourth order divided by 4. And that's it. The important point not to forget about is that in Cartesian coordinates, the surface is x multiplied by y, therefore dx multiplied by dy is the differential surface. In cylindrical, you would have to think, or in any curvilinear coordinates, you have to think about the volume or the surface that the element has, because it could depend on the coordinates. That's why they are curvilinear. So this is something I wanted to carry out. We will need calculations like that a little bit later. In fact, again in conjunction with inductance. And that's the last point I will make today. I have revealed to you that we have something which is called inductance. It is defined in different manners, but still we have the same inductance. We could define it energetically, dynamically, statically. Then we have, let's say, two kinds of inductance: self-inductance and mutual inductance. In fact, there is one more type of classifying inductances, and that is internal and external inductance. Those terms refer to very old works of IEEE fellow Professor Terman, and the idea is more or less this. For some applications, typically with AC currents, typically with high frequency AC currents, we can consider only current flow on the surface of conductors. The current that does not enter the conductor significantly. And therefore, the inductance value is only affected by magnetic flux that flows outside of conductors. This is called external inductance. And we have established a value of external inductance of a coaxial cable just today. But for some low frequency or DC cases, we can have magnetic flux also inside conductors. And therefore, for the same set of conductors, let's say a coaxial cable, there would be at least two values of inductance, one for high frequency, the other for DC. And the difference between those two inductances is called internal inductance. That's the inductance of a conductor that is resulting from a magnetic flux flowing inside the conductor. To be able to establish it, we will need a calculation like this, and we will need it 1 week later. That is next Tuesday. Just remember, please, that I have left you with a quest for a static problem which has got three charges, one positive, two negative ones, that are symmetrically positioned with the symmetry of this axis Z. The charges are of equal quantity but different signs. This is positive, those two are negative, and the task is find out all coordinates, all positions on this axis, which is Z. So for all Z's, where the electric field is 0. Now we consider that those are the only sources in this universe and that the media is vacuum, so it's totally linear, isotropic, stationary and homogeneous. The charges are so small that we can neglect their dimensions against the distance. I would wait the solution at my email skvor at Faculty of Electrical Engineering cvut.cz. Just some small exception. This is a competition, so I will not reveal the solution during consulting hours next Monday. But if there is no solution by next Tuesday, I will help you a little bit. And then we will see. Ladies and gentlemen, are there any questions now? So, if there are no questions, I will leave you some time before the seminar, which should start in 10 minutes. It's been a pleasure to lecture for you, and see you again next week.